Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 39, Using Textures in Shaders. Since we've started talking about textures, we've had two major accomplishments. First, we created a texture class, which uploads image data to the GPU and stores a reference to the associated texture object. In the previous video, we added UV coordinate data to each of our geometric objects, and those UV coordinates are stored in attributes, and they'll be used to determine which colors from a texture are associated to which points on a surface. Now, it's time to combine those two concepts and start writing shader code. So to begin, we need to talk about something called a texture unit. And this can cause a little bit of confusion. Texture objects, they store the pixel data. They also store related data like the different algorithms you're going to use to select colors from the pixel data. Now, sampling refers to this process of how you calculate a color of a fragment based on this information that's stored in the texture object. Sampling is the process. Something called a texture unit actually performs this sampling calculation. It performs sampling, and the texture object which it's going to sample from, the texture object is assigned to a texture unit. Now within the shaders, there's going to be a new uniform type of variable. Since it's a new type of variable, we'll need to update the uniform class in just a moment. But these objects are called sampler2D objects. And in this variable, we store a reference to this texture unit, which will sample from a texture. Within the shader, we'll also use a function called texture2D. And this takes two parameters as input, the sampler2D, which is the texture unit, which stores the reference to the texture object, and also a vec2, which stores the UV coordinates, which says which point we're going to get from the texture object. The function texture2D performs that sampling calculation, and the output is a vec4, which stores the color, the RGBA data. Now, technically, there's going to be a limited number of texture units that you can use at any one time. We're using a version past OpenGL 3.0, and according to the specification, we're guaranteed a minimum of 16 texture units. So we could use at least 16 units within any given shader. You could use more. It depends on how many texture units your hardware or your implementation supports. But texture units are different from texture objects. You might have hundreds of different texture objects in your 3D scene. However, when calculating the color of a particular point, you're only guaranteed to use at most 16. I don't think in practical purposes you'd typically use more than 3 or 4. All right, so in order to use texture units, there's another OpenGL function you'll need to learn how to use called GLActiveTexture. And what that does is it activates a texture unit. What that means is when a texture unit is activated, anything which has been previously bound, any texture object that has been bound by the OpenGL function GLBindTexture, that object will be assigned to the texture unit. Now, these references are all OpenGL constants. And there's GLTexture0, GLTexture1, GLTexture2, and there's as many of these constants as is supported by your system. So at least 16. Now, in order to use these more easily in our code, even though we don't know what the value of this constant is, we do know that for any positive integer n, GLTexture n is going to be equal to GLTexture0 plus that value n. In other words, the values of these constants, they are a consecutive set of integers. And that will be helpful information in the code we're going to be soon writing. Another function, which we might as well implement now, is called GLBlend function. Since you might use a texture which supports transparency, this function is used to configure how transparent colors are combined. So if you have one color which is transparent that you're overlaying on top of another color, how should you combine the RGB values? It's going to be some weighted linear combination of those two colors, and source factor and destination factor say what the coefficients of the colors will be in that combination. And these two parameters, they're again specified by OpenGL constants, and these say what the factor will be calculated in terms of the alpha components of these colors. So they include GL source alpha, GL1 minus source alpha, that would take the alpha component of the source and subtract it from 1. The destination alpha, you could do 1 minus destination alpha. You could just do a constant of 0 or a constant of 1. Although if you're blending colors, you might not want to do that. All right, so with knowledge of this function, let's go ahead and let's update some code. So heading back to our graphics framework, let's begin by updating the uniform class so that it supports this new type of variable, sampler2d. Within the core directory, let's open up the file uniform.py, and now it's going to support a new type of data, which I'll represent in the comments by saying it now supports a sampler2d. So what does that mean to support a new type? Well, when we upload the data, we have to explain how that works. So maybe I'll add this in the upload data function. In that big if-else block, I'll make this right before the else clause. Else if self.dataType equals sampler2d. Again, this is a little bit confusing because of the way texture objects and texture units work. We have to associate a texture object to a texture unit, and then we pass the texture unit into the variable. So the way this works, we actually need to store two pieces of data in this kind of uniform, both the texture object and the texture unit. And so assuming that the data field stores those two values, we'll separate them out first. So let's say texture object reference and texture unit reference self.data. I love this Python syntax. It separates out the two elements of those array, of that list, into those two variables. Okay. So the steps that we talked about before, first we have to activate a specific texture unit, GL active texture is the OpenGL function we need to use. And again, we're going to use that observation that GL texture 0 plus whatever this unit reference is. This combined will give us the value of the correct OpenGL constant. Now that that's active, we need to associate the texture object with the texture unit. We do that by binding the texture. So next, let's associate the texture object with active texture unit. So this is GL bind texture to GL texture 2D, and whatever the texture object reference is. All right, we're almost done. This associates the object with a reference, but we haven't actually passed the reference to the shader yet. That's the third and final step. So we're going to upload the texture unit number to the uniform variable in the shader. And in this case, we actually use GL uniform 1i because the texture units are just integers. Right, so self.variable ref, whatever the pre-calculated reference of that variable was, we're going to upload the number of the texture unit. And just the way the syntax works, all we really need to upload is this integer value. We don't really need to upload the OpenGL constant to the shader. So this is just texture unit ref. All right. So those are all the additions we need to make to the uniform class. And again, since we might start wanting to use some transparent textures, we're going to make a new addition to the renderer class as well. So within the renderer class, to support transparent textures, or translucent textures, we'll specify, first we have to enable blending, and then we have to specify the formula that'll be used in the blend function. So that's with GL blend func. That's GL, we'll do the source alpha. Right, so that'll be multiplied by whatever the source color is. And then the destination color will be multiplied by GL1 minus source alpha. Right, so some percentage of the source color plus the remaining percentage, 1 minus alpha, of the source color. This will be multiplied by the destination. Those will be added up. It will create a great blending effect. All right, now save those changes. We're going to create our new material, which is going to support textures. So this will go in the material folder. Let's right-click and make a new file. And let's save this one as TextureMaterial. TextureMaterial.py. All right. So we're going to be extending the material class. So we'll start with from material.material import material with a capital M. And we'll need some OpenGL constants. So from OpenGL.gl import all the things. And this class will be called TextureMaterial. All right, for the initialization function, we'll assume that all texture materials support a texture. And optionally, we'll be able to add some properties later if you want to change the default values of the uniform objects. As with all materials, we need to write the vertex shader and the fragment shader, and then we'll pass those into the init function of the superclass, of the material class. So first is vertex shader code. And let's see, we need our standard uniforms. So uniform mat for projection matrix, a uniform mat for view matrix, a uniform mat for model matrix. We have incoming data. We have incoming vec3, the attribute vertex position. And now we also have an in vec2 vertex UV. In this case, if we're using textures, we won't mix textures and vertex colors, so we will not add an attribute variable for vertex colors. Though I suppose you could if you wish. Let's see, and then we'll have an outgoing vec2 storing the UV coordinates, and those will be interpolated for us. All right, time for void main. All right, again, the most important job to be done is to calculate GL position. And we get that by multiplying our sequence of matrices. Projection matrix times view matrix times model matrix times, let's build a vec4 out of vertex position and add the homogeneous fourth coordinate 1. It's a long line of code right there. Zoom out for a second. And so we need to set GL position. And of course, we also need to take the incoming UV coordinates and copy them into the outgoing. So they'll get interpolated by the fragment shader, and we can use them in the fragment shader. So then we'll also add in UV equals vertex UV. All right, and that's it for our vertex shader code. Next up, we need to write, well, of course, fragment shader code. Fragment shader code equals triple quotation marks. All right, so we'll have a uniform vec3. We will use a base color in case you want to tint the textures by multiplying by some value. Now, this will default to white, so if you don't set it, it won't change the color of the texture at all. So we'll also use our first sampler 2D. Right, and this is going to store the reference to the texture unit. I'll just say texture for short, corresponding to this out variable UV. In the fragment shader, we'll have an in vec2 UV, which we'll use when we sample from this unit. And we always need an outgoing vec4, call it frag color. Now let's proceed with void main. All right, vec4 color. We'll start off with, we'll take the base color. We'll extend that into vec4. And then the color, we'll multiply that by, this will be the new function texture2D. So taking the texture unit and sampling from those UV coordinates. Then the result is frag color. All right. Or I guess we could even, shorten this up a bit. We could say frag color is equal to the base color times texture2D. And I guess we could shorten it even more, and we don't really need to define color, but we'll stop there. That looks fairly legible. And that's our fragment shader. All right, once we have vertex shader and fragment shader code, we are now prepared to call the superclass dot init function. We have to supply that with vertex shader code and fragment shader code. All right, once that's done, we need to add all the different uniform objects. Right? And you might recall in the uniform class, let's see, I guess we haven't added this yet. To simplify adding uniforms to objects, it might be nice to have some kind of an add uniform class or add uniform function. So let's create this in the uniform class. And so maybe right after def locate variable, let's define something called add uniform. This corresponds to add attribute in the geometry class. And so this will take data type, variable name, and then the actual data as a 3 parameters. Again, very similar to what we did with the add attribute function. Then we'll say self.uniforms. Right, under the key variable name, that will be a new uniform whose type is data type and which stores the data object. This will make writing uniforms or writing materials a lot easier. the process of adding uniforms. All right, with this addition to the uniform class, let's go back to the TextureMaterial class. Okay, so self.addUniform. Right, we'll add a vec3 called base color. And by default, we'll let that be white. And next, we'll add the uniform for the sampler 2D. And we call that texture. And remember, the sampler 2D needs to store two pieces of information. The reference to the texture, but also the reference to the texture unit. So the texture object reference and the texture unit. The texture reference we'll get from this texture that's passed in. Right, so the first parameter here will be texture.textureRef. And then we can just choose any texture unit we want, as long as it's not already in use. But since this is the only texture, we can pick whatever number we want. We'll use texture unit 1, that's fine. Next, we need to locate those uniform objects. So locate uniforms. Cool. We also need to set up the render data as well. So, as always, we want to check to see if we want to render both sides. We typically will. So in the settings dictionary, double side we'll call it. We'll default that to true. Not TextureMaterial. We'll default that to true. Then we'll say, do we want to render triangles as wireframe? Not sure why you'd want to do that with a texture, but you never know. Settings, we'll call this parameter wireframe. That'll be false by default. Line thickness for wireframe. And depending on your computer, it might support thick rendered lines, and it might not. So just in case it doesn't, all computers do support a line width of 1 by default. All right, and in case you want to change the default values of any of these parameters, like if you want to use a color other than base color, right, we're going to call setProperties on the properties parameter that was added to the top. So if you change any of those, it'll update these as needed. All right, finally, we need to tell the class how we would want to update these render settings. Right, you might recall in the base material class, there's defined a function called updateRenderSettings. And in the base class, it's just given a pass, it's up to the extending class to implement this function. And it depends on whatever settings we've added up here. So this might look familiar. Right, if self.settings, I think we use something similar for the surface basic material. So if this double side, if that's set to true, then we'll disable culling faces. Else, we'll enable culling faces. And culling faces is removing the ones on the back side. All right, if self.settings wireframe, and if that's set to true, then the polygons, the triangles, will be rendered, and this will apply to both the front and the back sides, will be rendered with lines. Else, the polygon mode, both front and back sides, will be rendered as filled polygons. And then finally, we'll set the line width to self.settings, whatever number is stored in here. All right. And that completes the TextureMaterial class. We're going to be able to use this to render textures and scenes pretty soon. All right, an excellent addition to our framework. In the next video, we'll actually put all of this material together and we'll start rendering some interesting textured scenes. Thanks for watching.